Okay, so I'm going to call this video section 2.1 part 2 because we've already gone over how to find break-even points, and today we're going to look at how to find the minimum or maximum of a function. So we're going to review quadratic functions again, and you should know that the general form of a quadratic is y equals ax squared plus bx plus c, and you should know that the graph is a parabola. And when it opens up, it's because this leading coefficient a here is positive. And when it opens down, it's because this leading coefficient here is negative. And also wanted to remind you that sometimes you'll get a parabola or any kind of function. It could be negative x to the third. But if you have any kind of negative x to a power, you have to type in the understood 1 or XL will give you an error. So if you have negative x squared, you're going to type in negative 1 times x squared, or using cell references, negative 1 times a2 squared if cell a2 is where your x value is. Okay, so we want to find the minimum or the maximum of a parabola primarily today. And so what I have drawn here, this blue line is a line that is going through one point on this parabola. And so this blue line has a negative slope. And this black line is going through one point on this parabola. And this black line has a positive slope. And so when we are finding the arc, if we can get the 2 points really close together, it's like finding the slope of this tangent line here. And so if you want to know where a minimum or a maximum is, you want to look for where your arc, or your average rate of change, goes from a negative value to a positive value, because somewhere there is an arc that has a slope of 0. Well, why is a slope of 0 so important? Well, this orange line is going through the vertex, and it has a slope of 0 because it's horizontal. And so what we know that is, if you have a slope of 0, you have a horizontal line. And the only place that you can go through a point on the parabola and be a horizontal line is at a minimum or at a maximum. So if you look for an arc that's really close to 0, what you've done is you've found 2 points that are so close together and in such a spot that there's a horizontal line. And if you have a horizontal line, a slope of 0, then you have a maximum or minimum. This method is very tedious, and because we have two better methods, don't emphasize this method very much. I wouldn't really want you to use this method on a test, but it's important to talk about it because it aids our understanding of what's going on with the calculus. The second method is the one we're going to concentrate on. And if you're given a quadratic in the form of y equals ax squared plus bx plus c, remember that you can find the vertex, you can find the x-coordinate of the vertex if you use negative b over 2a. And then once you find that x-coordinate, you substitute into the function, and you would use xl to find the y-coordinate if you need it. And that's the method that we're going to use. The drawback to this method is it only works for quadratics. Only quadratics. So very quickly, I just created a cubic polynomial. And the cubic polynomial I graphed is y equals negative 2x cubed plus 12x squared plus 134x minus 720. And it's degree 3. That's why it's called a cubic polynomial. And you can see that it has both a minimum and a maximum. And I mentioned that this slope of 0 here doesn't tell you whether it's a minimum or maximum. So that's a problem. But furthermore, you can't use negative b over 2a for a cubic. You can only use it for a quadratic. So I just wanted to show you a quick way to use the arc, how you would use the arc. So I set a domain from negative 10 to 14, and I typed in my cubic function right here. And then I have a column for arc here, and I colored this cell black because you never type the formula in the first cell. Start here at the second cell, and then the formula for arc is y2 minus y1 over x2 minus x1. So here's our y2 in B34 minus B33 over A34 minus A33. And then notice here the parentheses. Parentheses in front of the B34 and after the B33 because you have to help Excel understand order of operations. So you want to do this first, divided by parentheses A34 minus A33. If you forget the parentheses, it'll divide B33 by A34 and then subtract this minus this minus this. That's not what we want. We want it to subtract the numerator, subtract the denominator, and then divide. So the parentheses are important. So leave this blank, type in your formula, you drag it down, and notice that this arc here is negative 24 and this arc here is positive 36. So somewhere in here is an arc of 0 between negative 3 and negative 2. But here's the problem. That's not a maximum. If you were asked to find the maximum, the first thing you get to is a minimum. So you have to use what I call the eyeball method. You have to graph. So I would select this and graph this cubic polynomial. And the eyeball method, not very sophisticated, but it works. You can see that there's a minimum here between negative 5 and 0, and there's a maximum of that blue function here between 5 and 10. So once I know that the maximum is occurring between 5 and 10, around 7, then I'm going to go keep looking, and I see a 36 here and a negative 24 here, and that is where my maximum is located. Okay, then this takes a while, but what I did is, and I'm going to delete all of this and show you how to do it again. What I did was I knew it was between 7 and 8 somewhere, so I just typed in 7.1 all the way through 7.9, and I looked at these arcs, and they're all negative, but at 7.2, that's where I have my closest value to 0. So what I'm going to do is going to click on the 59, right click on the 59 and insert, and type in 7.15 because that's in between 7.1 and 7.2. And now I'm even closer to 0. Okay, so I'm going to go to 59 and insert, and what's between 7.10 and 7.15? How about 7.12? And that's a positive 1.3 and a 0.05. So I'm going to go to this 7.2 and insert. And what's between 7.15? 7.175. See what happens there. And I get negative 0.98. I want to try to get it to the hundredths place. So I'm going to go in between the 7.12. See what's happening. 7.13. Okay. Now these two are really close together. I'm going to insert. Just inserting in between these values, and I only do this once just to show you how tedious it is. Okay, and that's good enough right there. So I can approximate, this is only an approximation when you do this after all this work, that there is a slope of 0 happening around 7.14. And so this is where the maximum is. The max is at x equals 7.14. Okay, so to sum up this cubic polynomial, I had to fix a typo here, but it's correct now. Arc equals 0 at both the max and the min. We know that. We cannot use negative b over 2a with the cubic polynomial. You can only do that with the quadratic. So pre-calculus, or before we use calculus, you would have to graph it, visualize where the max is, and then look for the arc in that area, which is what I showed you how to do here. Okay, so that's not my preferred method. We're going to use the quadratic method of x equals negative b over 2a for quadratics, and I'll show you how to do that soon. But I wanted to go through the rest of this, the last way is to find the max or the min is to take the derivative and set it equal to 0. We're going to learn about this superior method in Unit 2. This method works for any type of function you would have. Quadratic, cubic, quartic, any kind of function. Okay, so this first example I'm not going to go over. There's a key in the second sheet, but it is a review, and the review, you should know how to write a revenue function, and you should know how to write a cost function given 2 points, and you should know how to write a profit function, and then you should know how to use Excel to find the break-even point. So go ahead and try that, see if you remember how to do all that, and then you can check this key here, and I have a few tips that you could work on if you need to. Alright, so we want to start with example 2. It says the amount of carbon dioxide in pounds per 15,000 miles released by a typical SUV depends on its fuel efficiency according to the formula, and the formula is given there, and where X is the fuel efficiency of SUV and the units are miles per gallon. This is my Math English dictionary. It's what I refer to when I want to interpret my answer. And then W of X says the amount of carbon dioxide in pounds per 15,000 miles. So that's my dependent variable. CO2 in, and the units are pounds per 15,000 miles. And this function is a quadratic. It's got a positive a value, so it's going to open up. And the question is, what is the fuel efficiency of the SUV with the least CO2 pollution? So we want to graph this and find the minimum. So I'm going to type in my function, 32 times x squared minus 2080 times x plus 44,000. And I want a window, so my x is fuel efficiency. Don't think that needs to be negative, so I'm going to start at 0 and count by fives. And graph it by selecting column A and B, insert, scatter with markers only, and there is my graph. It's a parabola. It opens up like I thought. And so we want to find the minimum here. Okay, so we know that the minimum is a little bit closer to 30 than 40, but it's somewhere between 30 and 40. And so you could use the arc method, or you could remember that this is called the vertex, and so there's a way to find the vertex of a quadratic when it is in quadratic form. We can find the x coordinate if we remember negative b divided by parentheses 2 times a. Using parentheses so that I get used to helping Excel with the sideways division. So I'm going to come over here and somewhere in here. So I'll just type in equals negative 1. I always type my understood 1 in because I never know if Excel is going to have trouble with that. So negative 1 times negative 2080 is my B, divided by parentheses 2 times 32 is my A. And that is an x coordinate, and so I will insert it. So click on the 20, insert 32.5, and there is my minimum. So where is the x? Where x is the fuel efficiency of SUV in miles per gallon according to the model. What is the fuel efficiency of the SUV with the least carbon dioxide? So I found the smallest y value. So here's where my Math English Dictionary comes in. When the X, or fuel efficiency, is 32.5. What are my units? Well, I wrote it down right here. Miles per gallon. Then the least amount of CO2 is produced. And I didn't ask you, but if you were asked, you could write the answer, which is 10,200. And I'm looking right here at my dependent variable units, and I know that it's pounds per 15,000 miles. Alright, if we look at the key, you can see I've done it another way here. This is the arc column. Remember, you never put anything in column 1. We want all of these values to make sense, so putting it here would make this end value not make sense. So I typed in the formula for arc, dragged it down. Notice that at 30 you had an arc of negative 320, and at 35 you had an arc of 112. So somewhere between the 30 and the 35 was an arc that is 0, and I just meticulously inserted a lot of these values until I was able to find 32.5, and I stopped there because that was good enough. Now you may be wondering why this arc isn't 0 here. Well, the arc is 0 at the tangent. If we could get really close to each other, so that it was almost like 1 point, and then this arc would be 0. See right here how this arc between 32.5 and 32.5005 is really small. That's what's happening, is these 2 points are getting really close together. So this method is like a clunky way to do calculus, but we're going to do calculus in Unit 2. So we just do this to sort of illustrate what we're heading toward is a tangent line. Instead of finding the arc between 2 points, we can find the arc between 1 point, which makes no sense, and it's not called arc, it's called instantaneous rate of change instead of arc. So you can look and see at the arc method, and then I showed my work for finding negative b over 2a here. Okay, read through example 3, including the questions A through D. This example has to do with independent variable t, which has been zeroed out years since 1994, and China trade in billions, which I've called t. And we want to find a quadratic function for the years 94 through 2024. This is what's called a closed interval. I'm giving you the domain. Only look between these years. The answers might be at the endpoint. So we have an endpoint at 0 and an endpoint at 2024, which would be 30. And so you have to look in that closed interval and beware that the answers might be at the endpoints. We want to find the minimum and find an average rate of change, and use goal seek to find when China trade equals 500 billion. So to start, you take your data that's given and you insert a scatter plot. And it's only 3 points, and it says create a quadratic model. So when I right click on a point, and a quadratic is polynomial order 2, I'm going to get an r-squared value of 1 because only 3 points. Quadratic model's a perfect fit. But notice that it's in y equals ax squared plus bx plus c form. And so the next thing I'm going to do is I'm going to leave this data, and you could start over or continue to use the column T that you started and create another called predicted trade. And just for emphasis, I'm going to black this out just so you remember that you just do not use the actual data once you have created a model. And I want my equation to, my domain to be exactly what it's been asked for. So I want my domain to be from 0 to 30 from the years 1994 to 2024. And so I will type in the function. And so that's it. Those are all the values. So now I can answer questions. If you want to, you can insert a actual years table. And the way you would do that is, you know, it's years since 1994. So if you do 1994 plus that column, then when you drag it down, it's going to give you all your years. Okay. All right, so now we're ready to answer some questions. A, use the model to find the value of U.S. trade with China in 2000. That would be the year. It would be the T value 6 years after 94, and so that answer is 120.2 billion. Next question, find the minimum. You can kind of look at the graph and see that it's close to 1994, and you can look at the lowest value here, and it's pretty early on. But remember, we have an exact way of doing this because it's quadratic. We can do negative b over 2a to find the x value. So I'll come all the way down here, and my not here because that's my actual year. Right here is where my independent variable is. So I'm going to do negative equals -1 times b, which is -4.5, divided by parentheses 2 times a, which is 2.7. So I'm getting my b and my a value from the equation. And then if I drag this value down one more time, I can see that this is 1994. If I unhighlight that, you can see that it's the actual year 1994.83. But the answer is, what's the minimum value of U.S. trade? So the answer would be the y coordinate, $48.125 billion. And then the next question, find the average rate of change between 95 and 97. So here is my x coordinate for 97. Here is my x coordinate for 95. Here is my y coordinate for 95 and 97. And so if I just wanted to do the arc here, I'm going to put it here. Now you have to skip over this cell because this has nothing to do with the arc between 95 and 97. So parentheses, my y2 would be here, minus y1, close the parentheses, divided by parentheses 3 minus 1. And that's the formula for finding the average rate of change between 95 and 97. So you have to skip over this point here. Okay, and so you get 6.3. Now to interpret that, I went through that in another video, but average rate of change, the very first thing you want to state is the interval, because we know the slopes are going to change depending on the interval. So you have to say between 1995 and 1997. You would not do the average rate of change. That is wrong. That's what some people do, but that's just repeating what I'm asking you to interpret. You want to make sure you interpret without using the words average rate of change. The way you interpret is, you remember, average rate of change is the difference in y's over the difference in x's. The y's are the dependent variables, trade in billions of dollars. The x's are years. Okay, so you could say something like the trade with China, because that's what this dependent variable, this function is, the trade with China, and 6.3 is positive. So you could say is increasing by 6.3, and the units are billions of dollars. So $6.3 billion per, and the x-coordinate unit is year. So we have the interval where this arc is happening, the name of the function, trade with China, that's the y, that's the name, the dependent. It's increasing by y, per means divided by, 6.3 divided by 1 year, per 1 year you could say, but that's understood. So that's the interpretation for arc. And the last question, when will China trade equal 500 billion? So this is a goal seek, and so remember that with a quadratic you might have two answers, because 500 billion is happening way up here, and you've got this parabola that looks like this. This is really awful, but forgive me. So you could have the answer here, or you could have an answer here. Okay, so you have to help Excel out, because if you drag this down, it's going to think that there's 0 here. And so when you goal seek, in fact, I'll do it for you. So we want to know, when will China trade equal 500 billion? Data, what if analysis, goal seek, change cell D37 to 500 by changing the independent variable here. It's going to start looking at 0, and it's going to look left and right, left and right, left and right, and it's going to stop looking as soon as it finds a value that satisfies it. But the problem is that's outside our closed interval. So again, you want to put a guess number in. So there's my 500. It's got to happen somewhere between 10 and 20. So I'm going to put a guess number in here of 15. And then I'm going to goal seek to 500 by changing 15. And so when you do that, you're saying, hey, Excel, would you look at around 15, left and right of 15, and then you can stop when you get close. And so it stops at 13.77. Now we need to know when, what year. So if we drag this down, we've already figured out that if we add 1994 plus this, we can get the real year. So the real year is in 2007. China trade will equal 500 billion. The next example is page 135, number 26 from the text. You can read it here. We are given a demand equation. Q equals negative 2P plus 320, where Q is the number of buggies and P is the price. So because of the position of the P, it's being multiplied by negative 2 and then add 320. That's the independent variable. And the questions are, at what price should it sell the buggies to get the largest revenue? And what is the largest monthly revenue? So this question is asking you to build a revenue function. So that's kind of review. So what we want to do is we want to make sure that we use P as our independent variable, and P stands for price. And so what I've done here is I have actually thought about how much a buggy costs, and I use that to sort of figure out my domain. And so I decided to start at 0 and count by tens. And then Q, quantity, is an equation, negative 2 times P plus 320. I drag that down. And then my revenue function, I just built it using Excel. So revenue is price times quantity. So I clicked on equals A2 times B2 and drag that down. And I can now start to answer the questions. At what price should it sell the buggies to get the largest revenue? So revenue is a function that I want to look at the graph. So what you can do is go to P, hit Control, and then go to R, and insert a scatter plot, and that's what I have here. So now you can see that revenue is a quadratic, and so the maximum revenue occurs here. This is my y coordinate, this is my revenue, and so my maximum revenue is going to be between 12,000 and 14,000, and the independent variable is price, and that's occurring somewhere between 50 and 100. Now we can find the maximum revenue, the largest revenue, in two ways. You can use the arc method, which is what I did here. I have the formula y2 minus y1 in parentheses divided by x2 minus x1, and I dragged it down, and I noticed that I can visualize the maximums maybe around 75, between 70 or between 80 and 81, or 80 and 90 is what I had originally. I can see that arc went from positive to negative. So here I just inserted a lot of these, and I was able to use arc to get the approximate maximum. But remember, we said we don't want to do that. So remember, when we built revenue functions, that's where this also becomes handy. We need a algebraic revenue function to be able to find the a and the b, so we can use negative b over 2a. So remember, to do this, we let p be independent. Revenue is price times quantity. And if you remember, p is independent, that goes in the parentheses here, and that reminds me that this q needs to go away. And so you're going to replace the q with negative 2p plus 320. And then if you multiply it out, you get negative 2p squared plus 320p. So now I know my b value is 320 and my a value is negative 2. So negative b over 2a is, right here I did it, negative 320 divided by parentheses 2 times negative 2, and I got 80. And so now I don't have to deal with this arc. I know that the largest revenue happens at 80, and the largest monthly revenue is 12,080. Okay, and then the last example is number 27 from the text. You can read it. In this particular one, it says that if the company builds 40 houses, then it can sell them for 200,000. And if it builds 60 houses, it can sell them for 160,000. It says obtain a linear demand equation and determine how many houses Pac-Man should build to get the largest revenue. So we need to create a function. Now, what's on this screen here is I've done this two ways. The first way is I've done what we typically do and let p be the independent variable, the price be the independent variable. So I put my p in the first column and my q in the second column. And remember, what you want to do is grab these points, insert a scatter, and remember, it does it wrong when your order pairs are vertical. So to fix it, you do switch row column. Okay, so that's what I have here. And p is independent. And you might pick that because typically p is independent, but I just want you to know that this one's going to work out better if you let q be independent because of the question. It says determine how many houses. So we want to know how many q's. So we could do the whole problem the other way and put q as my independent variable and p as my dependent and get a function. So you can do this either way you want to. If I go back to this one, once we have the equation here, notice how small this slope is. That's concerning to me because I only have one significant digit. You could make the decimals longer, but look at this function. See how that's better? So it really just is a better idea to let q be the independent variable. And so I'm going to go ahead and go with this one, and you can look over this first one and compare. if you'd like, but let's just do it this way. Okay, so we read through the problem and we decide Q is independent and P is dependent, and we get our function here, which I recopied here with the right variables. And you need to build a revenue function. So revenue equals P times Q. And so we want to have an R of Q function because we decided Q was independent. And so that means we need to get rid of this P by substituting in this equation here. And then you get an R of Q equals negative 2,000 Q squared plus 280,000 Q. And now we have a polynomial, a quadratic in ax squared plus bx plus c form. And so we can answer the question, how many houses to get the largest revenue? So we're looking for a max. Now I didn't do it here, but I'm going to go ahead and graph the revenue function because it's always a great idea. But before I do that, let me show you what we'll do next. Is you want to put this function in, so that's what I did here. And you have to set this domain. And so Q is quantity, and I can tell from the problem 40 houses built, 60 houses built, so I know that 0 to 100 is a pretty good domain. So I'm going to select my domain, hit Control, and select my revenue values and insert a scatter. And there's my quadratic. So what we're looking for is the maximum revenue, the largest revenue. And since this is quadratic, I can use negative b over 2a. So negative 280,000 divided by parentheses 2 times 2,000 would give me the x coordinate of 70. And so this is where the largest revenue occurs. This is the largest revenue. And then it doesn't ask, but what if it asks for the price? Well, I've got a demand equation I put in here that if I know the quantity, I know the price, so I put that in there, and this would be the price, 140,000. Okay, so this is the final answer here. They should build 70 houses to maximize revenue, which would be $9.8 million. You can check it. You see over here you get the exact same answer if we let P be independent. I chose prices from 100,000 to 160,000 and did negative b over 2a with this function here. 140 is my b, negative 0.0005 is my a. Found the p coordinate, and then if I want to find the quantity, I would plug the q equation here and get 70. So it works both ways. Okay, that's all the examples that I have planned, and so just to sum up, remember when you're typing a negative x any kind, I like to do -1 times the cell reference just to make sure Excel doesn't make a mistake. We talked about given a quadratic, you can use x equals negative b over 2a to find the x coordinate of the maximum or the minimum. We talked about how you really should graph your quadratic to see, kind of eyeball where the maximum or minimum is located. There's only one in a quadratic. There's a minimum and a maximum in a cubic, so that makes it especially important to graph. I like this method for finding the max or the min of a parabola. However, you could use arc, and so I kind of went over the formula for arc again and how you can use it to find the arc of 0. We also interpreted arc in an example, so that's very important. And we will get to taking the derivative and setting it equal to 0 in another unit, but we need to remember that the reason the arc is 0 tells us where the minimum or the maximum is because the slope of a tangent line is 0, is a horizontal line when it's the slope is 0 when a tangent line is horizontal. So you can find maxes and mins if you look for the arc of 0. That's not my preferred method. I would use the negative b over 2a method for quadratics. We will deal with cubics in the future chapter.